Welcome to Chapter 10, C Structures, Unions, Bit Manipulation, and Enumerations. Now, we're not going to cover everything in this chapter. We are only interested in C structures. And that is basically sections 10.1 to 10.6. So structures are sometimes also called aggregates. And structures are collections of variables. And we put them into this one larger, structure because for the purpose of the application, those variables are related somehow. Now, the key difference between structures and arrays is that structures can contain within them variables of different data types. Arrays are also collections of different variables, but with the condition that they all be of the same data type. And that is why structures are often found being used to store records. And not just keeping them in memory within structures, but also writing them to files afterwards. And that is something that we will get to very soon in the very next chapter, chapter 11, which deals with file processing, writing data to files and reading data from files. And the use of pointers, which we are by now familiar with, pointers allow us to do something else with structures. We can have structures contain pointers to other structures of the same or different types. And that allows us to build data structures whose names you may have heard of, called linked lists, queues, stacks, and trees. Data structures is the subject of a whole different course. So we will not go into chapter 12 that deals with data structures in C. However, if you're interested in looking at this use of data structures and how to build these different data structures that I just listed, linked lists, queues, stacks, trees, then you should take a look at chapter 12. And while looking at structures, we'll also look at the typedef keyword, which is used to create aliases. So we'll basically be using the typedef keyword together with structures to, in a sense, we'll be doing something with it that will, in a sense, look like we are creating our own data type. And here's a look at a very simple example of a structure. Structures are basically derived data types. They're constructed from objects, variables, often of simpler types. So here's an example. Let me show you with that. So this is an example of a structure called card, and within it are two character pointers. One is called face, another one is called suit. The keyword struct is also new, and that is how we indicate that we are about to, in this case, define a new type of structure. And this one's called card. So card is kind of like, over here, the name of think of it for the moment as the name of a new data type in a sense. Card is called the structure's tag or structure tag. The two pointers that you saw inside the structure are called its members. Now, the members within a structure must have unique names, meaning two members cannot have the same name. You'll see why in the example that we'll do. Also, another thing that I must note, kind of like the do-while loop, the definition of a structure ends with a semicolon. Let me go back and show you. Point this out here. Don't forget to place the semicolon at the end of the definition of a new structure. That is, initially at least, a common mistake and will give you a syntax error. Now, in the example that I just showed you, the structure card had two members, face and suit, of type character pointer. But you can really have anything in there, any primitive data type, meaning integer, float, any of those basic data types we are by now very familiar with. But they can also contain other aggregates, meaning you can have arrays inside a structure. You can even have other structures inside a structure. And not only that, the members of a structure can be of many different types. And here's a slightly more elaborate example. So I mentioned that we often use structures to maintain records. So let's take this very simple example where we are maintaining the record of employees, and we have a structure over here called with the structure tag employee, and within it we have a character array called first name, size 20, another character array called last name, also of size 20, and then we have an unsigned integer age, we have a character gender, and we have a double precision floating point number, hourly salary. And this is the exact same syntax that we just saw for the card structure. Now, one thing that a structure cannot contain is an instance of itself, meaning a structure cannot contain within it a structure of its own type. That would be recursive, and that is not allowed because the structure that you're including would then have another structure of its own type in it, and that would never end. I'm sure you can understand that. So the example of this negative example, or one such negative example is given on this slide. So over here we have a structure struct employee2. Structure tag is employee2. We still have the first name and last name character arrays of size 20. We still have the unsigned integer age, the character gender, the double precision floating point number, hourly salary. But if we try to add in a structure of type employee2 in here, let's call this instance person, that will most definitely give you an error, because that structure will have within it another structure of type employee2, and that must within it also have a structure of type employee2, and this would go on forever. And it can't. So this inclusion of another structure of type employee2 within a structure of type employee2 will give you an error. However, what you can do is you can have a pointer to a structure of type employee2 in there. That is absolutely fine. And that is the basis of the data structures that I listed before. If a structure contains a pointer to a structure of its own kind, like I just showed you in employee 2. That is permitted, and such a structure is called a self-referential structure, meaning a structure that is referencing or pointing to another structure of its own kind. And like I mentioned, that's the basis of data structures that are introduced in chapter 12. Now, when you define a structure by itself, that does not take up any space in memory, okay? Because you're not putting any data into it. It's kind of like saying, so structure variables like that are kind of defined like variables of other types. And here's an example of how you could do that on a single line. So over here we are using one line of code to define a structure called a card, an array of size 52, where each element is of type struct card. So this goes together. And on the same line, we are also defining card pointer, which is a pointer to a card structure again. You can do all three on one line. You could do the same thing for a primitive data type. It's not good practice, of course, but this is just to show you that you can define structures just like you can variables, individually as arrays and pointers to them. Now, you can also define a new type of structure without giving it a name. You can give it a name, but you can also do without. So you can even define instances of a structure at the time you're defining the structure. So here's an example. For example, when we were defining struct card with these two character pointers as members, face and suit, before ending the definition with a semicolon, it is possible to define the individual structure A card, the array of type card of size 52 called deck, and the pointer to a struct card. You could define them right there where you're defining your structure card. That's also valid, perfectly valid syntax. And if you're defining all of your instances, arrays, pointers of that structure type in that one place, even the use of the tag name becomes optional. So if you wanted to, you could skip giving this structure a name over here. You don't have to include the tag name card in here. The downside of that, of course, is that in that case, you can not declare any further structures or pointers to that type of structure later in your code. You can't have separate declarations of those types of structures. And for that reason, it's always good practice to provide a structure tag name when you're creating a new structure. And it is definitely needed if you're going to declare new variables of that structure type later in the program. Now, the only operations that you can perform on a structure are assigning structure variables to structure variables of the same type. So assignment, taking the address using the ampersand operator, accessing members of a structure, and using the size of operator to determine the size of a structure. But what you cannot do, you are not allowed to compare structures with the comparison operator, equal to or not equal to. And the reason for that, and I'm not going to go into too much detail for that, is the reason for that is that members of a structure are not necessarily stored in consecutive bytes of memory. Could be that one member of a structure is located in one place in memory. So let's say face, for example, and for the same structure, the suit pointer is stored someplace else, and in between you have other stuff. So it's not like an array where, let's say, you have 3 elements of an array that you know that they're all going to be located right next to each other. And that is a requirement if you want to do comparisons of this type. So there can be what we call holes in the data structure. So this over here, this memory location, this space between the face and suit members of a structure would be considered a hole. Then there are also considerations that different computers, different platforms will use different ways to store data members of a structure. So for example, consider this structure example containing a character C and an integer I. And let's say we create 2 instances, sample 1, sample 2. Now, character, of course, takes only up 1 byte. Integer can take up 2 to 4 bytes. So let me quickly jump to a visual representation. Maybe this will be stored like this on a computer, which means we don't know what's going to be in here. And if we have 2 different structures, sample 1, sample 2, we have no idea of knowing what's going to be in this hole in between. So comparisons do not remain possible then. Okay. Structures can also be initialized at the time instances of them are being defined, just like arrays. And here's an example of one such initialization. So over here, we are creating an instance of struct card called a card. And at the same time, we are initializing its 2 pointers, suit and face, with face and suit in this case. So 3 with these 2 strings, 3 and heart. Just like for arrays, if there are fewer initializers in the list, then you have members in the structure. The remaining members will be automatically initialized to 0, or if the member is a pointer, to null. Structure variables defined outside a function definition are initialized to 0 or null if they're not initialized explicitly. And structure variables can also be initialized in using assignment statements by assigning structure variables of the same type. And I'll show you an example in which we do that. Now, how about accessing members of a structure? There are two ways to do that. First one is the structure member operator, which is just the full stop character that you have on your keyboard, also called the dot operator. And the second one is the structure pointer operator, which is a dash or minus sign followed by a greater than sign, which makes it look like an arrow, which is why it's called an arrow operator. Now, structure member operator accesses structure members by the variable's name. So, for example, if you've already created a structure variable called acard, like we've done a couple of times now in preceding slides, you could access the suit pointer in it, the character pointer in it, like this. But if all you have is a pointer to a structure, then you have to use the structure pointer operator. And in that case, let's say we have card pointer, a pointer to a structure of type card. In that case, if you want to access a member of the structure it's pointing at, you use the arrow operator. Now there's if this arrow operator seems a bit strange to you and you're more comfortable with the dot operator over here, you can still use the dot operator if all you have is a pointer to access your structure. And in that case, the syntax is going to be like this. Now, you see the parentheses over here? Those are not optional. You have to use those because you want to make sure that the dereferencing, the pointer operator is applied first and the dot operator is applied after that. So this is an issue because of the order of precedence of the dot operator before the dereferencing or pointer operator. And you can do the same thing if the structure that you're referencing, if that is member of an array, you have to add the square brackets to that. Okay, so let me show you a simple example in which we use this card structure to create an instance of the card structure called a card, and we assign face pointer. We point the face pointer to a constant string ace, and the suit pointer to a constant string spades. And then we not only assign these values, we also access them using both a pointer and the structure variable name acard. Let me jump to the code. So over here, we define struct card. That happens, as you can see, outside before the main function, which means that this structure type has a file scope, meaning it can be used anywhere in any function within this file. In the main function, I define a struct card variable called acard, and then I assign its members, face and suit, the constant strings ace and spades. Here I want to point something out. These two strings are constants. They haven't been defined as character arrays anywhere else before this. And for that reason, because of the way I'm doing this assignment over here, I need to, because of the way I'm using the card structure, these pointers actually have to be declared to be pointing at constant strings that cannot be changed. So there's a slight error over here. So I have to add the const keywords before the character pointers in the card structure. We then also define a pointer to a struct card called card pointer, and we initialize it to the address of a card, this guy over here that we already defined earlier, and to which whose members we already point at these two constant strings, ace and spades. Now let's access these members. And we do it in three different ways. First, we access the members directly using the dot operator, so a card dot face and a card dot suit. That's one way to access members of a structure. Then we can use the pointer to that structure, card pointer, and using the arrow operator, and that looks like this: card pointer, arrow operator, face. Card pointer, arrow operator, suit. And then the third method is to use the pointer but use the dot operator. And in that case, we have to use these parentheses. So pointer operator, card pointer, in parentheses, dot face, and the same thing for accessing suit. Pointer operator, card pointer, in parentheses, dot suit. When you run this code, you'll get this as output. This is one access to one member, access to the other data structures data member, and this is using the second method using the arrow operator, and this is using the pointer with dot operator. Structures can be passed to functions by passing individual structure members. And the thing to remember is that structures are passed by value. That's a key point. If you want to pass a structure by reference, you can do that too, but in that case, you have to choose to pass the address of that structure. If you want to pass an entire array by value, you can do that using structures by sticking that array into a structure and then passing that structure, of course. You can also kind of do the reverse of that. You can have arrays of structures. And like all other arrays that we've seen, in that one, that array containing structures as each of its element, that will be passed by reference, meaning only the pointer to the first structure will be sent to the called function. And like I mentioned, you can use this trick or this property of passing structures to functions to pass an array by value by sticking it inside a structure. Because structures are passed by value, so the array inside them is also passed by value. Finally, there's the typedef keyword. Now, the typedef keyword, short for type definition, is a mechanism for creating an alias for previously defined data types. And the way we would use that together with structures is kind of like this. So let's say, so far we've just been using, we defined this struct card, but if you want to treat this struct card with a lowercase c over here, if you want to treat that like a data type, a new data type that you created for your application, you can add the typedef keyword in front of it, and after that you can provide another name that you want to give to this type of structure. So maybe with a capital C over here. And then card will be treated like a new data type that you created. And you can do this, you can do that while you're defining your new while you're defining a structure like this. You can skip the use of the structure tag name, lowercase card with a lowercase c. You can do it like this in one go. So basically just add the typedef keyword before struct and put the name that you want to give your new type of variable, your new type that you're defining. You put that after the curly braces, before the semicolon. And just as what we typically do is we capitalize the first letter of typedef names to emphasize that they actually mean something else underneath. So in that case, that would simplify the definition of an array of the structure. So before that, we had to type struct card dec 52 to create an array, for example. This can now be done like this. The typedef card with a capital C space dec 52. Kind of like you would define an array of type integer of size 52. You can see the similarity. Instead of int, we have our newly defined structure typedef structure card over here. And that looks a little more natural, I guess. Also makes for easier to read code, perhaps. Okay, so this is sometimes also used to make code be more portable across different platforms, because the basic data types on different platforms can be different. And yeah, that's but we're not going to go into that. That's not in our scope over here, but now you know what the typedef keyword does as well and how to use it effectively together with the use of structures.